Okay, let's look at the proof of the uniqueness theorem. Okay, so you already saw one proof using the contradiction. Now we are going to look at a direct proof. Okay, because there are things to learn from this one also. Okay, so here we start the proof by also assuming there are two limits, L1 and L2, but here we don't assume that they are not equal. Okay, so the goal is to prove that they are equal. So if we say there are two limits and they become equal, then also we can say the limit is unique. Okay, so here if we think what's going on, we look at from a different angle this time. So here we know our sequence as go along the sequence, later terms of the sequence keep getting closer to L1 because L1 is a limit, but they are also getting closer to L2. So that means L1 and L2 should become closer because we can make the terms close as we wish to both of them. That means they should lie very close, so we should be able to get L1 and L2 close as we wish. Okay, so this is our plan, and for this type of a proof we can use triangle inequality. Okay, if you recall that here what's going on, A is getting close to B, also C is getting close to B, no? Then A and C should get close to each other if we think according to our normal situations. That's happened. So this type of a thing you can capture using triangle inequality. Okay, we'll use that somewhere in the proof because of this thing or behavior we expect. Okay, so now we'll move on to the proof. So when you are doing a proof, also always help to think what are the definition of given things and what is the definition of what we have to prove and how to connect them. Okay, so we know that we take that An has two limits, L1 and L2, maybe they are equal this time. So if L1 is the limit, we know from the definition for any given epsilon there is a n. If n is greater than n, A minus L1 is less than epsilon, no? So it's for any epsilon. So theoretically here we can put epsilon over 2 also because any epsilon. Same way for N going to L2, we can get these statements 320 and 321 because of these limits. Okay, why we are putting epsilon over 2? Hold that thought for some time, you will get the answer at the end. Okay, so I want to use both of these statements in my proof. So both of them work if I go, this one work n1 greater than n2, any n value greater than n2. This one work any n value greater than n1. So if I take the maximum of them to be n, if I choose a m bigger than that maximum value, I can apply both these statements 320 and 321. There is a mislabeling, I'll correct it, okay, later. So now with this we use a little trick that enables us to use the triangle inequality. Okay, so here I have L1 minus L2. I take the modulus of this, okay, and slip AM in the middle. Now remember that both 320 and 321 applicable for this AM, no? Now I use the triangle inequality here. I can break it down like this. This part become greater than or equal to the top line, no? So because these two are equal, this one becomes greater than or equal to L1 minus L2. Now I can use that 320 and 321, say these are less than epsilon over 2. Here I get epsilon. Okay, even that's why I put epsilon over 2 before. Actually I do if you are someone doing the proof for the first time, they will go when here they say epsilon, to make it nice and have epsilon here, they put epsilon over 2, no? This is theoretically possible to put epsilon over 2 there, no? Okay, so even you don't put epsilon, even you get 2 epsilon is fine. Okay, So it's up to you. Now here I have L1 and minus L2 less than epsilon. If I had 2 here, I have 2 here. But even though I have the 2 or I don't, it doesn't matter. I can make epsilon more as I wish. No. So here it's saying this modulus of L1 minus L2 is less than epsilon, and this is a positive value if it's non-zero. No. Now that cannot happen, because if it's a positive value, I can pick epsilon less than that. If I cannot do that because of this statement. For any epsilon, this is less than that. So that means L1 and L2 have to be equal. Okay, from this I can conclude L1 equals L2. Actually, you can prove that fact. I put it as exercises to you to try. If two numbers are given and they are different, modulus value of their difference is less than any given epsilon, you can prove they are equal to each other. Normally, now on in theorems, you can use this observation directly if you have to. Okay, but this exercise you will have to prove it using a contradiction. Okay, little hint, or any other way, standard way to prove it using a contradiction. Okay, so I'll stop here.